justifying standard justifying standard parameters in the TLS 1.3 handshake. Hannah, can you hear us?
I can. Hello.
Hi, we can hear you as well.
Okay, can you see my screen?
Yes, we can.
Okay, great. Okay. Hi, my name is Hannah Davis, and I'm here to talk about practical security bounds for the TLS 1.3 handshake protocol and why it matters to security that the encoded length of the legacy session ID of a client hello message does not begin with the bytes 3, 6, or 5C. This is based on work by Dennis Diemert, Felix Günther, and Tibor Jager. The Tls Handshake is a key exchange protocol that helps two parties negotiate a secret session key over the internet. The most recent version, TLS 1.3, is now default for more than half of the top 1 million servers. Most TLS 1.3 users, including me right now, use the full handshake protocol, which uses public key certificates for authentication. There are also two pre-shared key modes that use symmetric key authentication, mainly for session resumption and low-power devices. The prior security proof for TLS 1.3 by Dowling et al. Reduces to the security of its building blocks. For the full handshake, these include a Diffie-Hellman group, a cryptographic hash function, and a digital signature scheme. The TLS standard gives several options for each of these parameters, targeting different levels of efficiency and security. In this talk, we'll measure security in bits as the ratio of an attacker's runtime to its advantage, which is the probability of successfully breaking the scheme. So an instance of the TLS 1.3 handshake that prioritizes efficiency might choose faster components with 128-bit security, like the X25519 elliptic curve. A higher security configuration might instead use a 192-bit secure curve like SecP384. For an arbitrary configuration, Dowling et al. Proved this theorem. It says that for any attacker with limited resources, including runtime and the number of honest sessions and users that it can see and interact with, the probability of learning anything about the session key is bounded by the sum of one term for each underlying cryptographic primitive and a small constant term. Each term in the bound has two factors. One that bounds the probability of breaking the underlying primitive, multiplied by a function of the adversary's resources. Because these multipliers are all polynomials, we say that TLS 1.3 has asymptotic security. Asymptotic security means, in practice, that we can achieve any security level we desire by using large enough parameters and scaling them up appropriately. We can see this in practice by fixing an adversary, a hash function, and a signature scheme, and looking at what happens as we expand the size of the underlying Diffie-Hellman group. However, scaling up in practice isn't really a feasible option because the TLS standard only offers a few choices of group and a few choices for each parameter. So we're less interested in the slope of this graph than about its values at 5 specific points corresponding to the 5 standardized elliptic curves. And even among these curves, a vast majority of users will use the most efficient options, the 128-bit curves. So we thought it made sense to look at the concrete security guarantees that the bounds offer at these specific configurations. We start with an example fixing a specific 128-bit configuration and a specific relatively weak adversary with 2 to the 60 runtime, 2 to the 20 users to interact with, and 2 to the 35 sessions. When we plug these numbers into the Dowling bound, Dowling et al., sorry, we get an advantage upper bound, a maximum probability of breaking the protocol. To put this number in context, let's set a security goal. With all 128-bit secure parameters, we'd like for the handshake itself to also have 128-bit security. Using our runtime over advantage definition, this translates to a 2 to the negative 68 advantage bound. And we can see that we're just barely over the line. So we're not quite meeting the target security. As we look at more powerful attackers, the story gets worse. With runtime up to 2 to the 80, we're missing the target upper bounds by a substantial amount. And for our most powerful attacker, the bound actually only guarantees that a break will happen with probability less than 1. This is not what we want. We're missing the guarantees that we want because the reduction to the Diffie-Hellman group underlying TLS 1.3 isn't tight. The S squared term here means that we have a quadratic loss in the total number of TLS 1.3 sessions, and there are billions of sessions happening each day, so this loss is substantial. Our main contribution was giving a tighter bound for both the full handshake and the pre-shared key modes that reduces this quadratic loss to a constant loss. And we can see that for all of our adversaries, we are able to achieve the target 128-bit security and well under that. These improvements extend to all of the other standardized elliptic curves where we performed the same type of concrete evaluations. And we can see that even when prior security bounds do meet the targets and do guarantee the desired levels of security, we can still improve on them by up to 80 bits of security. This is for the full handshake. We also performed the same type of evaluation for the pre-shared key modes with a Diffie-Hellman key exchange and achieved the same caliber of results across the board. Finally, we looked at pre-shared key only configurations, which don't involve a Diffie-Hellman group. And while we were able to achieve tighter bounds when the hash function is chosen to be SHA-256, for SHA-384, our methods failed, and we'll talk about why that happened closer to the end of the talk. The quadratic loss that the Dowling et al. Bound has is a common issue in Diffie-Hellman-based key exchanges like the TLS 1.3 handshake. So let's dive a little more into that. The decisional Diffie-Hellman problem gives an attacker two random elements of a cyclic group called the Diffie-Hellman shares, G to the A and G to the B here. Then the attacker must distinguish between the Diffie-Hellman secret, G to the AB, and a random third element of the group. To build a key exchange based on this problem, we let a client and server each sample Diffie-Hellman shares and exchange them over a network. They then derive a session key from both shares and the associated secret using a key derivation function. In a key exchange model, an attacker doesn't expect to see just one session, but many sessions happening simultaneously. A reduction to the Diffie-Hellman problem therefore has to simulate all of these sessions at once, even though it's still only being given two shares, G to the A and G to the B. Historically, the only way to do this that was known was to pick one random client and one random server to embed the shares in and hope that these two sessions would be attacked by the adversary. This is where the quadratic loss comes in, a random factor over the number of sessions for picking a client and a random factor of sessions for picking a server. The issue that leads to this quadratic loss is called the commitment problem. But in a crypto paper in 2019, Cohn-Gordon et al. Came up with a solution for the commitment problem that they applied to some specially designed key exchange protocols that had three important properties. First, they reduced to the strong Diffie-Hellman problem instead of the decisional Diffie-Hellman problem. Strong Diffie-Hellman is an interactive assumption where an adversary is given the two Diffie-Hellman shares and an oracle for the DDH problem that solves a restricted variant. It then has to compute the Diffie-Hellman secret on its own. Changing assumptions to achieve a tighter bound is generally an ill-advised strategy, but we're not actually doing that here because the prior bounds for TLS 1.3 depend implicitly on strong Diffie-Hellman through the PRF ODH assumption. The other two requirements for the Cohn-Gordon method are that the key derivation function should be modeled as a random oracle, and it should have both Diffie-Hellman shares and the Diffie-Hellman secret as inputs all at the same time. These two requirements extend a little less naturally to TLS 1.3. The key schedule for TLS 1.3 is not a single key derivation function, but it's instead used to derive 11 keys using a series of chain calls to the HKDF extract and expand functions. The Diffie-Hellman shares and secrets never enter the key schedule at the same point. So to use the Cohn-Gordon methods, we have to abstract this key schedule into the random oracle model very carefully. We actually did this twice in two concurrent analyses of the TLS 1.3 full handshake. Our first way of doing this by Davis and Gunther were to model HKDF extract and expand as two independent random oracles. Although we still don't have the shares and secrets entering at the same point, we connect them in our proof with a careful lookup strategy that exploits the distinct labels in almost every call to expand. Unfortunately, that model is pretty unrealistic because if we look at the definitions of extract and expand, we'll see they're both very closely related to the HMAC function, and they have highly correlated outputs, so not independent at all. Our other method was to, by Diemer and Jager, was to view the path through the key schedule for each type of session key as an independent random oracle. So they have 4 independent random oracles modeling these overlapping paths through the key schedule. And the advantage of this method is it's clear how it matches the Cohn-Gordon requirements. There's one key derivation function for each key, and the shares and secrets enter properly. This allows a much simpler proof, much more elegant, and it avoids all of the lookups and dependence on labels. However, it's hard to see why these overlapping paths are independent themselves. When we extended our techniques to the pre-shared key models in an upcoming paper, we had to pick between these two abstractions. But while trying to do so, we noticed that they have a common issue. In the random oracle model, you should typically replace one hash function with a random oracle everywhere that it's used. But TLS's single hash function is used outside the key schedule and in it as part of the HKDF functions to shorten transcripts before they enter the key schedule and as part of the message authentication codes. In order to use an abstraction that's both realistic and gives us tight bounds, we want to replace H with just a single random oracle everywhere, but also preserve these independent key derivation functions from the Diemer-Jager model. And we want to more carefully justify our abstraction so these issues don't pop up again. We can achieve all of this in the Indifferentiability Framework. This framework from Maurer et al. Allows us to give a bound that bounds the difference between the real TLS protocol and an abstraction of it in the random oracle model. And we start with a very simple step, one hash function to one random oracle. We then split this random oracle into 2 pieces, one for hashing transcripts and one for doing all of the other hash operations in TLS, HMAC, HKDF, etc. We then treat HMAC itself as a single random oracle, relying on some prior work by Dodos et al. And then we split it into 11 random oracles, 12 in total, including the transcript random oracle, using the same lookup strategy from our earlier proof. The advantage here is that it's now a standalone proof instead of one that's embedded in a key exchange proof. The step we didn't justify is a little bit more subtle. And this is where the legacy session ID comes in. To prove indifferentiability, we need a rule that determines when a hash function input is a transcript and when it's not. So as a quick example, is this a transcript or not? For this one, we can tell because it's 71 bytes, which is too short to be anything but a transcript. All HMAC calls are at least 96 bytes in TLS 1.3. When the hash function is SHA-256, transcripts can be at more than 96 bytes. So we need another way to determine. And in this case, we diagram out an HMAC call and a client hello message, the start of a transcript. An HMAC call starts with 32 bytes of key, and then 32 bytes that is padded to a specific value, either each byte being fixed to either 3.6 or 5C. In a client hello, we have 34 bytes of version number and nonce, and the first non-random byte after this is the length encoding byte of the legacy session ID. In order to tell that something is not a transcript, we need to check this byte, byte 34, and verify, does it match 3.6 or 5C or not? And for a valid transcript, it will never match either of these values because the legacy session ID has a maximum length of 32 bytes, which is convenient, but it's also lucky. And we're only this lucky for pre-shared key only modes with SHA-256. When the hash function is SHA-384, there's no such luck, and we can't find a hard and fast rule to distinguish between hash function inputs that are transcripts and that are not. This is why we weren't able to give type bounds for the pre-shared key only mode with SHA-384. We do give proposals for potential domain separation fixes for protocols like TLS that use a hash function in HMAC and in other places. And we hope that this will allow us to eventually give this type of tighter bound for all modes. Thanks for listening to this talk, and I'm happy to take any questions.
Thank you, Hannah. If someone has any question, please come to the mic in the middle.
Yeah, thank you, Hannah. That was a really cool talk. If you were just starting from scratch, how would you redesign TLS 1.3 to get rid of all these kind of weird random oracles and the bad domain separation? What would you do differently if you were starting today?
Oh, this is where I mentioned that we have proposals. There's no perfect answer because starting completely from scratch would involve also redesigning HMAC to allow for some domain separation between the internal hash function calls of HMAC. And then a design of TLS would include labels in these underlying HMAC calls as well. Without that being possible, I would probably include some suffix padding to each of the hash function and HMAC and HKDF calls within the key schedule to try to separate every single hash function call. This would greatly simplify the domain separation steps, and the modular indifferentiability approach really does simplify the actual key exchange portion of the proof.
Could you not get rid of HMAC and just use SHA-3 for everything?
You could potentially in some cases, but they are using HMAC as a message authentication code. And the key part of that is something where I'm not sure SHA-3 would be a perfect substitution straight off the bat.
Thank you. Thank you very much.
Hi, thanks for your talk. The improvement in the tightness that you did relies very strongly on this strong Diffie-Hellman assumption, but we're trying to move away from Diffie-Hellman in a lot of places. So do you have any idea if we could use the same kind of fix with a chem instead of Diffie-Hellman?
I'm not sure. The technique does rely quite heavily on the re-randomization properties of strong Diffie-Hellman. I'm not familiar enough with chem assumptions, especially for like post-quantum chems, to know if they have similar re-randomization properties, but it's always possible.
Thanks.
No other questions? So I don't see any on the chat right now. So maybe let's thank Hannah again. So our second speaker is there in person. So his talk is about Alpaca, application layer protocol confusion, and we'll welcome Marcus Brinkman on stage.
So how does this work? I have a thing here. Okay. So thank you for coming. This is a joint work with Christian Dresen, Robert Merget, who is here, Damian Podebniak, Jens Müller, Jura Zamorowski, Jörg Schrink, and Sebastian Schinzel. And our research is in real-world protocols like TLS. And last year, Robert gave a talk on a side-channel attack on TLS Diffie-Hellman, breaking its confidentiality. And this year, we show how gaps in TLS authentication can be used to break application security. So, TLS is the most important protocol to provide confidentiality, integrity, and authenticity for server applications on the internet. Here's an example, a web server and a browser. And it is also used to protect other legacy protocols, such as file servers with FTP and email servers with POP3, IMAP, SMTP, and other protocols. So let's take a closer look at how TLS achieves this portability. TLS is designed as a transparent layer between the network layer and the application layer. So the idea is that it is completely application independent. And in particular, TLS does not protect the TCP connection endpoint, such as the IP address or port number. So an attacker can, first of all, redirect the packets to a different service. Excuse me? This can sometimes enable application layer protocol confusion, where the client and the server speak different protocols, here HTTP and FTP, and this can lead to cross-protocol attacks. So in such a cross-protocol attack, the client is redirected to a server speaking an entirely different protocol, and we prevent these attacks normally by relying on TLS domain certificates who isolate each service from another, right? So in this case, if you have two completely different services, they have incompatible certificates, and the browser will terminate the connection after the attacker tries to redirect it. But sometimes there are gaps. And the man-in-the-middle attack is possible. For example, in the case of wildcard certificates, one certificate can be valid for all subdomains of a domain. And there are multi-domain certificates which are simply valid for many host names. And even on a single host name, if you have a certificate with a single host name, it can still be used across multiple services on that same host using different port numbers. So in this work, we consider only cross-protocol attacks on HTTPS, exploiting an application server speaking SMTP, IMAP, POP3, or FTP. But I want to make sure that you understand that potentially any TLS speaking protocol can be redirected to any other. So the number of possible cross-protocol scenarios across all TLS protocols and services grows quadratically, and we have not explored most of them. And we consider three different exploitation methods. So in a reflection attack, the attacker would try to trick the client into sending a malicious payload to the intended server, which is then redirected to another server, and that server potentially reflects this payload, for example, in an error message. In the download scenario, the attacker would first prepare the evil payload on the server that is redirected to, and then the client would download it from there. And in an upload attack, we try to extract sensitive data from the client by redirecting it to a protocol that can upload data. So to give a more complete example, here's the first cross-protocol attack on TLS applications by Jan Horn in 2015. And this is a bit complicated, but we walk through it. First, the attacker lures the victim on its own website, and then causes the browser to create a so-called cross-origin HTTP request. This does go to a different server than the attacker server, in this example, bank.com. And in this request, the attacker can put an FTP command. So then the man-in-the-middle attacker redirects that to the bank's.com FTP server. And the browser will accept this connection because there's a compatible certificate. It thinks it is talking to the browser, to the web server, sorry. And then the FTP server may be error tolerant, ignore the HTTP header, and then find this FTP command. And this FTP command is actually invalid, so it will create an error message that contains this JavaScript from the attacker. And if the browser is also tolerant to protocol noise, it may execute this JavaScript thinking it comes from bank.com. And in this case, it gives the attacker access. The attacker can impersonate the bank, basically. So here's another attack. This is a download attack, also by Jan Horn, in which the attacker prepares the JavaScript as a stored file on the FTP server. It's in the bottom right. You have to have some sort of access to the content of the FTP server to do this. And then, in this case, the FTP commands contained in the request will open a data port. And on this data port, there's a second request caused by changing the URL in the location bar will actually download this response. So in this case, the attacker can prepare a completely valid HTTP response, and there's no protocol noise, and this will always work. And in this case, also the attacker gets to impersonate the bank completely. We contributed a third attack method. In this case, we prepare the FTP server to accept an uploaded file, and this uploaded file then contains the HTTP header for any request going to the bank.com, and this can contain sensitive data such as a session cookie if the user is logged in. And this also completely breaks the web security model, because then the attacker can extract the cookie and impersonate the user to the bank. So we evaluated all these three fundamental strategies with all of the 4 application protocols that we looked at in the context of the browser, except where it doesn't make sense. SMTP is an email submission protocol. It does not support downloading at all. And POP3 is an email retrieval protocol, which does not support uploading. So we had to exclude these scenarios. And we had the following research questions. First, are these attacks still possible? I showed you an older attack from 2015. Is this still possible? Are there more attacks? How many servers are affected by cross-protocol attacks on the internet? And can we prevent them? So first, we evaluated the browsers for their tolerance to protocol noise, because if they detect that an FTP server is responding, we probably can't do anything further. We found that Internet Explorer and Edge Legacy are very tolerant and find JavaScript embedded in a lot of noise and execute it, while more modern browsers have filters that detect invalid responses and then they don't execute the JavaScript. So in this case, we can only work with methods that do not include noise, such as the FTP upload and download attack. And we looked at 24 application servers, speaking one of the 4 protocols, and looked for their tolerances as well. and found that in over half of them, we can at least find some attack vector that works in one browser at least. So in 13 cases, we can use download or reflection attacks in the Internet Explorer and its legacy, and in 4 cases, we can do all the attacks also in the FTP upload and download attack in all browsers. So then we wanted to see if there are servers on the internet that allow these attacks. And we have to go backwards. First, we have to scan for the application servers that are vulnerable, and then try to find the web servers that also can be accessed with the certificate of the application server. So first, we scanned for all application servers and found 31 million FTP or email servers that speak TLS. And of these, about 19.7 million have valid certificates that are accepted by browsers. So all these certificates are potential vectors for exploits. And we scanned these certificates for all the host names they contain, and found 2 million unique host names. For wildcard certificates, we had to guess, and we guessed www for the subdomain. And then we looked for web servers on those hosts and found 1.4 million web servers. So what this means is that for 1.4 million web servers, we can find an application server that has a certificate which the browser accepts for the web server. So the man-in-the-middle attack is possible. It does not mean that we can exploit this, but it means that TLS authentication is already bypassed. And then we try to identify these services if they are one of the vulnerable servers that we analyzed in our lab, and could still identify 114,000 web servers that we could actually exploit with one of the reflection, upload, or download attacks. And now I want to talk about the countermeasures. There are many countermeasures in the past, and often the first idea one has is to fix this at the application layer. So for example, postfix, there is an SMTP server that actually detects HTTP requests and will block the connection and terminate it. And another thing that's often done is to rely on syntax errors in the protocol, and then this is some sort of implicit unknown protocol detection, and that can also lead to a termination of the connection. There are also protocols that have, or implementations that have reduced the number of reflection vectors, so JavaScript can't be reflected, for example. But all these things can lead to incompatibilities. They can only prevent known attacks, and more importantly, they happen after authentication, after checking they happen after the Tls handshake. So there could be bypasses, and TLS can prevent them. So another idea is to enforce strict isolation for certificates. And this would mean no more wildcard certificates, no more multi-domain certificates, and only a single service on any host name. And this is just purely impractical and also expensive for administrative reasons. So it is unlikely that we will make any progress on this front in the near future. And so what we recommend is actually a cryptographic countermeasure in the handshake. And there is already a TLS extension called Lpn, it's application layer protocol negotiation, and this is almost a perfect fit. So this was not intended for security or to prevent cross-protocol attacks. It's intended to multiplex multiple protocols on the same endpoint. So for example, HTTP 1 and 2 are incompatible, but you can serve them on the same port because TLS allows to specify a list of supported protocols by the client, and then the server can select one and return this, and then both ends can agree on one of the protocols. The problem here is, first, we have to do this in the other server that is redirected to, right? It's not the web server, that's the problem here, but the FTP server. And these servers actually do not need ALPN at the moment, so it's often unsupported and they simply ignore this extension and just continue the handshake, ignoring anything that's given by the client there. So what we actually need is something called strict Lpn validation, where the server detects that this client is a web server, a web browser, and then sees that this web browser actually wants to speak HTTP and not FTP, and so it terminates the connection early. And this is our recommendation. We have made some progress. Some of the application servers have already implemented this and are slowly updated on the internet. So this is my talk. I will summarize shortly. The cross-protocol attacks are possible. We have identified 114,000 servers that can actually be exploited. And we have recommended strict LPN, and there's another extension, SNI, that can help a bit, that can prevent these attacks for all protocols and all scenarios. So what's left to do? There could be more cross-protocol attacks on other protocols, and there are also other security layers like DTLS and IPsec, which we have not looked at. So thank you for listening. If you need more information, there's a website. I just posted an update with newer numbers, so check it out. Thank you.
Thank you, Marcus. If you have any questions, please come to the mic.
Hello, thank you for your talk. I was wondering, in the scenario where the victim is visiting the attacker website, which seems to me like the most interesting scenario, isn't the attack limited by current course policies? I think most banks would not allow a cross-site request from another.
Okay, thank you for your question. Can I go back on the slide? I don't know. I don't know if I can open the slide again, but so the thing is, there are some requests which are cross-origin that are called course-safe. Like they are always allowed in current web technologies. They seem to be very important for compatibility reasons. And so the initial request always goes through. There are many limitations around this, like for example, it may not contain the cookie, or and the attacker cannot see the response. But what actually happens is that we can deal with these limitations. So in this case, for example, in the second scenario, I gave the example, the response is discarded because the attacker cannot read it anyway. And then this works. We have to navigate all these issues, but there are always some scenarios where it works and it doesn't work in all scenarios. But in fact, we can do more. In our paper, we also did the complete attack in some cases without man in the middle at all. So check it out. It depends on the cookie policies and in many details.
Okay, thank you. But in this particular case, it will not work because post is not course safe, right? Like it would trigger a pre-flight.
Post is course safe, yes. So you can control the header, but you can control the body. This is perfectly fine. If we have an implementation of this, you can download the source code and actually run the attack locally on your machine.
Okay, perfect. Thank you.
Any other question? Okay, so I don't see any question on the lip, but you can still ask them later if you want.
Thank you.
Let's thank Marcus again, please. So our next talk will be given by Mike Hamburg. So I don't know if Mike is online, but I think that the talk is recorded.
I'm here.
Yeah, okay.
Hello, everyone, and welcome to Improved Certificate Revocation List Compression with Structured Linear Functions. I'm Mike Hamburg with Rambus Labs. So the motivating problem for this talk is certificate revocation. So we all know what a certificate is. So this is a document that binds some party's identifying information to their public key for a limited validity period. And it's all signed by a trusted third party called a certificate authority. So to verify one of these, you need to know the CA's public key, you need to know what time it is, but also you need to know whether the cert has been revoked, which could happen for each cert at any time. A popular way to do this these days is called the Online Certificate Status Protocol, or OCSP, where conceptually you just ask the CA, hey, is this still valid? And they send you a signed response. If you were to have the client do this, it would have serious privacy and latency issues. But these can be mitigated in the context of TLS by having the server do the lookup instead and cache the result. It is, however, a single point of failure for establishing secure connections or whatever else you were thinking of doing with those certs. For example, in 2020, Apple's OCSP server went down. They were using it to validate code signing certs, and as a result, people couldn't launch apps on their own machines. Fundamentally, the Online Certificate Status Protocol also only works if the parties that are verifying the certificates are online. So, for example, if they are something like a connected car, which may have intermittent internet access, but might, for example, be going through a tunnel and not have it right now, then you can't easily use this to validate the certs of this car and other cars. An alternative approach that's much older and solves some of these problems is certificate revocation lists. So conceptually, the CA just publishes a list of the certs that they've revoked. They don't need to include the expired ones, and the client keeps this list up to date. And then when they get a cert, they can check offline and privately whether that cert was revoked as of the last time they updated the list. The problem, of course, is that there are a lot of certs on the internet, so these CRLs are huge, and they must also be distributed to all the devices on the internet. So you can tackle this problem using conventional compression technologies, but it's still a huge logistical challenge. An approach for improving this that has been discussed at Real World Crypto before and has now been deployed in Mozilla Firefox in telemetry mode is CR Lite. So the key observation of CR Lite is that with a conventional compression mechanism, the client would get at the end of the day a list of all the revoked certs from some certificate authority. But they don't actually need that. What they need is a way to decide, given some cert that the CA issued, whether that cert is revoked or not. And the CA only issued a limited number of certs in a given time period. So this is in some sense a problem of compressing a function that takes a cert issued by some CA in a given time period and returns either valid or revoked. So if you put suitable metadata on this compressed database, then the client will only query it for certificates that the CA actually issued in that time period, which either the CA or an aggregator, in the case of Firefox, this is Mozilla, can collect from CT logs or from their own logs. And so as a result, you only need to build a function that is correct when queried on elements of a certain finite predetermined domain, the certs that were actually issued. Because queries will not be made outside that domain, you don't have to care what answer the client would get if they did that. This can be more efficient than a CRL because fundamentally you're conveying less information. In data structures research, this is called a static function, and to the best of my knowledge, the state of the art in this area is what I will call structured linear functions. So here's how a structured linear function works. The idea is to encode the function as a hash function, doesn't even have to be a cryptographic hash function, and as a matrix M over some field. I'll tell you first how to query this map. The idea is that you hash your input with the hash function to get a sparse vector W over the same field. Then the query result is M times that sparse vector. You can evaluate this quickly because to multiply M by a sparse vector, you only need to look up a few coefficients of M. So if that's how you query this, how do you do the encoding? Well, we have these constraints on M, which is that it has to give the right answer for all of our predetermined inputs. So in other words, M times each W must be the corresponding answer. We can combine these into one linear system. M times the matrix of all the W's gives the matrix of all the answers. This is an affine equation with respect to M, so we can solve it, putting M here on the right and giving this transposed equation. Furthermore, you can note that if this matrix is roughly square, then the amount of information contained in M is going to be almost exactly the same as the amount of information contained in each of the answers. In that sense, the this encoding process will be nearly perfectly efficient with regard to the information content of the mapping you're trying to compress. So how does this work? So in the original proposal, matrix filters, the hash function returns a vector of a fixed Hamming weight k, i.e. it's 1 or non-zero over the field in k positions in each row, plus there's these augmented columns representing the answer. And then you solve this matrix using Gaussian elimination. Unfortunately, while the matrix starts out sparse, as you solve it with Gaussian elimination, it fills in, and as a result, the solution process takes approximately O of n cubed time and O of n squared memory. If n is the number of certs on the internet, or even the number of revoked certs on the internet, say in the millions, then n cubed time and n squared memory is impractical. You can mitigate this issue by breaking the database into smaller shards that can be processed more efficiently. However, this reduces the compression efficiency and increases complexity. An alternative approach proposed in 2009 is peeling. So using a very similar distribution of rows, but making the rows approximately 23% longer, i.e. making the matrix you're trying to solve 23% wider than it is tall, it turns out that you can solve such a matrix with high probability simply by permuting the rows and columns into row echelon form. This takes only linear time and linear memory. However, making the matrix wider than it is tall means that the encoding that you solve for will be longer than it would have otherwise been. So for example, with a Zor filter, you will produce an encoding that's 23% longer than the optimal encoding. Recent research has improved this down to as low as 7% with a 4-way binary fuse filter, but there still is this overhead. An alternative approach that trades off compression efficiency versus speed is ribbon filters. So the idea of a ribbon filter is that instead of hashing to a vector with fixed Hamming weight, you hash to a vector which is non-zero only in a certain interval that is randomly placed, or rather pseudo-randomly placed by the output of the hash function, and its contents are uniformly pseudo-random. When you sort the rows, which doesn't change the output of the solution of the matrix, then you get a matrix that is banded. And when you solve a banded matrix using Gaussian elimination, it doesn't fill in outside the band. So this makes the solution procedure efficient in terms of time and memory. However, there is a catch, which is that these banded matrices, if the band is too narrow, won't actually have a solution. This can be mitigated by making the matrix slightly wider than it is tall, enabling a trade-off of the width of the band, which increases the time used to compress the matrix against the compression efficiency. Today, I'm proposing a new solution to this problem, which is Frayed ribbon filters. So for this, you hash each input to a row that has 2 blocks of uniformly random values. The 2 blocks are usually right next to each other, but they may have a gap between them with decreasing probabilities for wider gaps. If you sort such a matrix, you'll get this blocky, because the blocks are, the intervals are aligned, blocky, frayed looking structure. It's not obvious that you can solve this efficiently, and in fact, with Gaussian elimination, it would not be fast, but it turns out that there's a specialized solution tactic that works for these matrices. So the idea is to pair up adjacent blocks and then solve them to systematic form. And then we can project them out of the rest of the matrix and recurse on the next size blocks. As we do this, the matrix fills in a little bit. Heuristically, it should have it should enable solution of nearly square matrices, so nearly optimal compression size in time that is around O of n to the 3 halves, though in practice it's dominated by lower order terms, such as moving memory around. So in comparison to previous work, this is suitable for both static functions and something called approximate sets that I will get to in a second. It has a much lower overhead than other previous work that is suitable for these things, other than the very slow ZOR filters or ZORSAT filters. And it has about an order of magnitude slower build time than previous work. However, queries are still quite fast. The build time might seem like a bad thing, but if you're only doing this a couple of times per day, then spending 1.3 microseconds per item isn't a problem. So in summary, we have an encoding for compressing maps that has nearly optimal efficiency, fast queries, and fast enough build times. And it scales to hundreds of millions of rows before you run out of memory. So it would seem are done in creating a better compression function for CR-Lite. However, we still haven't used a key fact about CRLs, which is that 99% of certs at a given time aren't revoked. And so actually the CRL has less information than 1 bit per issued cert. The amount of information contained in it should be described by the Shannon entropy, which is about 12 times smaller. So we would like to get down closer to the Shannon entropy. To do that, CR-Lite compresses its databases. So CR-Lite uses a primitive called approximate set membership. It uses specifically Bloom filters, and these are closely related to static functions. The idea is that you have a set S of objects and you want to compress it so that from the compressed form you can query whether an object was in the set. When you query it on an object that actually was in the set, it always will return yes. However, there are exponentially more objects not in the set, and if you query on one of those, in most cases the query will return no, it's not in the set, but there is a false positive probability epsilon. The size of the approximate set structure trades off against the false positive probability epsilon. So the trade-off for Bloom filters is not optimal. It uses about 44% more space than what you would get if you constructed an approximate set based on Frayed ribbon filters. In general, you can construct these approximate sets using any static function. So how CR-Lite uses these Bloom filters is that it stacks them in a cascade. So the idea is it creates at a first level a Bloom filter containing all the revoked certs in the data set. And so then when the client gets a cert and they do a lookup into this, if it says, no, this is not revoked, then because Bloom filters have no false negatives, then the client knows that indeed the cert is not revoked or was not as of the time that the database was compiled. However, if it says, yes, this is revoked, then the client doesn't know if it's really revoked or if it's a false positive in the Bloom filter. However, the aggregator, or the CA, if the CA is doing this compression, has a list of all valid certs that were issued during that period, and so they know a list of all the false positives. So they can construct a second Bloom filter, which contains all the false positives in the level 1 table. So if the client gets a positive in the first table, they can do a lookup into the second table to determine whether it was a false positive or a true one. However, this second table is also a Bloom filter, or an approximate set in general. And so it also has false positives. So we need a third level and a fourth one, and so on. These levels become exponentially smaller, and so you only need log n levels. In this new work, I propose using instead a 2-level cascade that takes advantage of both static functions and approximate sets. As in CR-Lite, at the first level, you build an approximate set containing all the revoked certs. This gives you some list of false positives and, of course, the true positives, which is the certs that were revoked. And then at the second level, you compile a static function that maps the false positives to 0 and the true positives to 1. Because the static function always gives the correct answer, you don't need a level 3. By tuning the false positive probability of the first level, you can guarantee that the size of this cascade is always asymptotically within 11% of the Shannon entropy of the distribution of values in the map. So this is for binary maps, that is, things that output 0 and 1, but there's a generalization to functions with any finite codomain that is still guarantees that the encoded size is within 11% of the Shannon entropy, although it may use more than 2 levels. I prototyped this system using Rust, and I've published it on GitHub. The prototype is MIT licensed, and it also uses a new research-grade matrix solver over GF2, which is very efficient and may be of independent interest. I wrote this because I could not find an appropriate F2 matrix solver that was MIT licensed. In comparison to CR-Lite, if you have, as an example given in the CR-Lite paper, 100 million certs, of which 700,000 are revoked, and you plug this into the new Frayed Ripon filter, then it takes about 12 seconds to compress it, which is about a quarter of the time that it takes to generate that many fake cert hashes at random. It takes tens to hundreds of nanoseconds to query and produces about 800 kilobytes of output, which is 6% over the Shannon limit. By comparison, CR-Lite produces about 1.3 to 1.4 megabytes of output. CR-Lite is also much slower to compress this database, but only because it's written in Python, because it doesn't really matter whether it takes a couple seconds or a couple minutes for a process that you're only doing once or twice a day. In any case, the Frayed ribbon cascade uses approximately 40% less space than CR-Lite. It accomplishes this about 30% by using Frayed ribbon filters instead of Bloom filters, and about 10% from using a 2-level cascade instead of an n-level cascade. There's still plenty of work that could be done. So one example that is not addressed here is incremental updates. So this is so far talking about compressing an entire CRL, but in fact, only a few thousand certificates are revoked each day, and it doesn't make sense for the clients to download an entire new, freshly compressed filter every day. It turns out that CR-Lite's Bloom filter cascade can be updated with Delta updates, but the update process is not very efficient and is not implemented in Firefox. But linear filters are not updatable at all, so what do? Well, there's a generic solution that's somewhat inelegant, but I think good enough, which is that each day you send down a dictionary of certs that were revoked that day. Since this is fundamentally the information that you're conveying by a daily update system, this has nearly optimal bandwidth usage, about 10K a day with these example specifications. The queries are probably also fast enough because, well, it's only taking hundreds of nanoseconds plus however long it takes to fetch a block on disk or flash per level of this. So per day since either the cert was issued or since you last downloaded a full update. So this is likely fast enough for TLS, but it would be nice to have a more elegant system in the future. Adam Langley has proposed Golem-coded sets for this purpose, so it would be interesting to do a comparison. We have some ideas for future work in this area. A lot of this is just the generic stuff like, well, there's a prototype grade implementation and it would be better to have a production grade implementation, or it would be better to have formal analysis of the whole process, in particular a proof that the matrices are always soluble with high probability. As well as incremental updates. There's probably a faster shape that you can make these matrices in, and is there any way to get that last 11% of the compression back? But in conclusion, I think CR-Lite has demonstrated that static functions are a great approach for distributing objects like CRLs and possibly also other security information like malware databases. And this new work improves the efficiency of that by approximately 40%. And it still has fast queries and fast enough build times. And I'm looking forward to future work that improves this even further. That's all. Any questions?
So, Mike, are you online for questions?
Yes, can you hear me?
Yeah, we can hear you. So if you have questions, please come to the mic. Question is coming, Mike.
Test. Hey, Mike. Really great talk. I was just wondering, a lot of your framing of this problem is sort of implicitly as an optimization problem, and it seems like since you have this very explicit kind of matrix formalism, like the formulation of this problem. Have you thought about explicitly using some kind of an optimization-based approach to phrase the problem of choosing an optimal matrix as some kind of a linear program, and then you can solve it using standard optimization techniques?
Yeah, so actually, the sub-step of choosing the false positive probabilities or other parameters of this cascade is a linear program. It's a special one, so you can you don't have to do a full LP solution on it. As for trying to make the matrix solver as fast as possible, the issue is that I don't have a formal proof of exactly in what cases the matrix will be invertible with high probability. So what I have instead is I just tested it on every block size up to several million blocks. So that is not something that I can easily apply an LP to.
I see. Actually, sorry, I have a follow-up question. Why does it matter if the matrix doesn't end up being invertible? Can you not just, can you use a seed to choose a new hash function and then try again?
Yeah, you could do that, but it has to be invertible most of the time, or else you take forever to compress.
Thank you very much.
Hi. So I noticed that the query time varied a lot depending on the method that was used. So there was the frayed ribbon method, and it was compared to the ribboning method and other things. What were the causes for the variance between the query times? Was it just matrix width, or was it hashing mechanism, or what?
It's a couple of things. The biggest reason is that I rewrote this in Rust. I had an initial C prototype, and I was like, oh, Rust is better for safety and whatever. And I was optimizing that on an M1 Mac, but then for consistency with the other tests, with the other filters that are optimized for Intel, I didn't want to be like, oh, on this one thing, mine's much faster. And for some reasons, Rust's SIP hasher crate is significantly slower on the Intel one and not on the Mac, and I didn't get that worked out before making the slides. So that is a lot of it. Also, the bigger number, right, has got multiple queries because it's got a cascade instead of only one. Instead of only one frayed ribbon filter, it's doing two of them.
Right. Okay. Thank you.
Welcome.
Thank you, Mike. I think there is no more questions. So can we thank the speaker again, please? So this is the end of the TLS session. Before leaving for the coffee break, please thank all the speakers again.